Dr. Johnson, and in this talk I'm going to address publication bias and meta-analysis and what I'll call other vexing issues. You'll see this is a difficult issue to address, but meta-analysis is one place where you can do it. So you'll see this icon of worshiping the grave of p less than 0.05 in this talk. And you'll see other disturbing metaphors like what happens to trials and what are they hiding, perhaps. So let's get going. So as an overview of the whole thing, here's the outline. I'll review biases in science that are based on using statistical significance as a norm. Put another way, that's the conventional null hypothesis statistical testing framework. Then most of the talk I'll focus on methods to deduce publication bias, plus complications, those vexations that are trying to resolve the biases. I'll have one slide with conclusions, and then I'll leave you with a few discussion questions. So, according to one source, there's research on all of these things. It turns out that studies that are statistically significant are more likely to be stopped earlier than originally planned and then published quicker. Those that are statistically significant are more likely to be published in English as opposed to non-English sources. Those with statistically significant results are also more likely to be published more than once. Again, if you're doing a meta-analysis, you want to try to correct for that problem at the outset. If they're statistically significant, they're also more likely to get cited by others. So as a journal editor, when I accept a very well-done trial with null results, or what's often called negative results, which is a misnomer, I'm hurting my journal citation rate, even though I'm doing the right thing. And then there's selective reporting of some outcomes, but not others. So that's selective reporting bias, depending on which direction of the results you get. So you basically can change things. It's like a primary outcome becomes a secondary outcome, or vice versa. And then, of course, there's publication bias, which is that statistically significant results are more likely to be published overall. But you can see from this set of biases, it's not a simple problem. Right? And it turns out that you could even see it across the hierarchy of sciences, such that the so-called softer sciences, the social sciences, are more likely to publish positive results, that is, results that are statistically significant, than are the hard sciences. Very provocative. So we've got this very strong norm going on in all of the sciences, but really especially the soft sciences. Now, here it is, a meta-analysis seminar, and you knew it was coming. You've got to think about formal hypothesis testing. So here's the set of norms. The null hypothesis could be true, that's this column, or the alternative hypothesis could be true, that's this column. And then you get a p-value from your test, and if it's larger than the alpha value, which is typically 0.05, then you do not reject the null hypothesis. If the p-value is equal to or less than alpha, then you reject the null hypothesis and you agree with the hypothesis you had to start with. So from this, we end up with a convention of type 1 errors versus type 2 errors. So type 1 errors would be basically a false positive. You're concluding there's an association when there is none. And a type 2 error would be the reverse. You're rejecting the alternative hypothesis even though it's true. This example that I pulled off the web somewhere a long time ago suggests that convicting an innocent person would be a parallel example in the courts and in the legal system. So that's a type 1 error. Type 2 error would be failure to convict a guilty person. My opinion, perhaps, but I would think type 2 errors are much more likely in our legal system, but that's beside the point. So as scientists, we tend to try to avoid type 1 errors, or we probably do tend to bend over backwards and reach type 2 errors instead. But the system has been widely criticized, and one of the more provocative critics is Charles Lambden at Intel Corporation, and there's an image of him from a few years back, and here's a more recent one that I just pulled off the web. But he calls significance tests as like sorcery. And so science is empirical, you get real data from science, but significance tests themselves are not empirical. Okay? And he's got a lot of reasons that we could go through. I'm not going to belabor it. In fact, in class I'll give you a handout, but I like to quote this particular line from his article that Cohen jokingly states he had to resist the temptation. This is Jacob Cohen, by the way, the famous statistician. He had to resist the temptation to call in NHST, which is null hypothesis significance testing, statistical hypothesis inference testing. I'll let you figure out the acronym, which presumably would have yielded a more appropriate acronym. So like I said, I'll leave it to you. I think you should beware of assumptions because it could make an ass of you and me. That would be the way Lambda would think about it. In fact, very big bodies have been focusing on this recently. The American Psychological Association had a whole special issue of the American Statistician Journal focused on moving to a world beyond p less than 0.05. And there are 43 papers in this. I found it rather ironic, although meta-analysis is mentioned briefly in this opening editorial. You don't see the word in the rest of the commentaries, at least I did not. I stand to be corrected if I'm wrong. In the meantime, we have other problems that have been exposed. In 1998, Norb Kerr published this provocative article in Personality and Social Psychology Review, and it was widely ignored through much of its early publication history. And then around the the teens, you see a rise. And in fact, if you update that sequence, he's got up to 1,500 citations for this work as of yesterday. So something happened. My sense is, it was published in a social psychology or personality journal. It was a new journal. Maybe it was looking for papers back then. I think people didn't want to admit the truth that, in fact, harking happens, that you could hypothesize after the results are known. Surely that can help our science, huh? So harking has caught on, has become a conventional word, and everyone should read this article because he's very compelling about the problems of being post hoc with your theorizing instead of a priori. Okay. Jonah Lehrer, who's had his own issues with credibility, wrote a very provocative article called "The Truth Wears Off." And he documents, I think that even if you doubt Lehrer for faking his own journalism, a lot of this is true. John Ioannidis is cited in here as, well, as scientists, it feels good to validate a hypothesis. It feels even better when you've got a financial interest in the idea or your career depends on it. Now you can see that, scientists are human beings. I mean, here we're meta-analysts, yes, but we're also doing meta-science. We're thinking, well, why are the scientists doing what they're doing? And there might well be economic reasons underlying them, which might motivate them to put results out that maybe they don't even believe are false, but are false. We hate being wrong. Okay? And he gives the example of hormone replacement therapy. You still see how, which has been debunked pretty much, and vitamins, stuff like that, the stubborn resistance. Stubborn researchers citing the very first few studies that show a strong effect, and they really want to believe that it's true. So, in fact, with Lehrer, he was documenting how a lot of times an effect is found, and then people have trouble replicating it. And so something was magic at the time the study was produced, and then boom, it's gone. So one of the first examples I can identify of this phenomenon is an article published in 1974 in the Journal of Social Psychology, JPSP. Paulette Gilligas was a student of Tony Greenwald's, and they did at the time a rather large set of work. I mean, it was not that easy to collect data back then, but Tony Greenwald and his student went out and they found 7 replications, over 600 participants in these, looking at the sleeper effect, which is that you get more persuaded over time after you've received a message from a non-credible communicator. And basically, they found null evidence. So poor Tony tried to replicate a classic study and couldn't do it. And he continued then to think about this. Even the next year, he publishes a Psych Bulletin piece, Consequences of Prejudice Against the Null Hypothesis, and lays out a lot of reasons why publication bias could occur. And he asks a very provocative question in this presentation here, which is, what if the journals were filled with nothing but type 1 errors? We try to trust our journals, but if you can't believe their results, because basically all you're seeing is the 1 in 20 studies, that's, 1 divided by 20 is that 0.05 alpha rate that we've been talking about, I think we're in trouble. This article, too, failed to get a lot of attention, although it's come up a little bit in recent years. I think no one wanted to think how the system could actually be biased. I mean, this is, again, scientists resisting the truth, perhaps, a classic case of denial. Anyway, Greenwald's paper has this nice flowchart in it, and I think the thing to highlight, you can go and read it yourself and get a sense of the complexities of how thinking about the problem here. Um, Obviously, you formulate a problem, you collect data, you write a report, you've got an editor's decision, and then you have to decide to try again if you fail. And at each point, you've got to make decisions. So in fact, you might formulate a hypothesis at the beginning. You might have the wrong hypothesis somehow. Uh, and you've got to do a lot of work to get to the point of having data, and then you've got to do a lot of work to write it. And each point, you've got all these choice points going along here. And you can see that even having it be published is not entirely in your control, because the editor and the reviewers are all part of it. And then you as a reviewer, as a scholar, have to decide if it fails, if they don't publish it, then are you going to try to get more data? I'd be curious to hear the back picture of this article in 1974, how many years it took to do that and how many times they submitted it before they finally got it in a premier journal. So there's publication practice, and what's emerged in the decades since then is that we have developed methods to deduce publication bias. So the first way, I would say, the most intuitive and really compelling in many ways to me, is to compare the results of unpublished published studies. Of course, if you don't select them into the meta-analysis in the first place, you can't do that. So those that are selecting only published peer-reviewed papers, they're walking right into publication bias, aren't they? So one of the first and most compelling demonstrations that this could be a neat strategy was a meta-analysis that Lipsey and Wilson published in 1993 in American Psychologist. And these are 92 different meta-analyses. So they compared published versus unpublished studies, and this is just the distribution of the effects. So you can see that the published studies were these are in the standardized mean difference metric. And these are interventions, psychosocial, behavioral, educational interventions. They had about 1,000 overall, and only about 10% of them offered this comparison of published versus unpublished. So this is an equal horse race. You're leaving all the other ones out in this comparison. So each of these, essentially, you can imagine that each meta-analysis has a point on both sides of the graph here. And what you can see is that published studies were indeed about, 20% or so larger in their average effect sizes compared to unpublished. So people are probably overestimating effect sizes routinely if they only use published results, at least in the intervention domain. And obviously this is a long time ago already, and it was a huge amount of work. That's an interesting paper too. If you want to dive into the history of this, I recommend that one too. Here's another way that's come out. You could compare published reports to those that were previously submitted to the Food and Drug Administration for drug approval. So, I mean, this routinely happens with any drug. And so you can now go and look at the reports. These are all public domain. You can get them by a FOIA, Freedom of Information Act. And here's maybe the most famous example of it. This is Eric Turner and colleagues published in the New England Journal of Medicine. They examined antidepressants. And indeed, in every case of all of these antidepressants that the FDA has approved, the estimates that the FDA had were significantly lower in effect size than were the published results. So what happened between FDA and publication? They were screening out the results. They were leaving them out because they were non-significant and therefore jacking the effect size up. A couple of them, the bias was quite large in favor of the treatment, and the overall was 32%. So I've given only examples in this particular. This is a fascinating paper. If you go to read the Turner et al., make sure to read the appendix, because that's where all the gnarly details are, but they're fascinating. Okay, funnel plots are out there, and you routinely will do this. I recommend it, especially in cleaning your data too. You want to see how your data look. You want to use the precision of the estimate, not the sample size. So if you look at this, here's an actual example that Lau et al. Published. If you look at the sample size, that's the distribution you get. It's not quite the same as precision. Here's precision. And so you don't want to do the first one, you do want to do the second. So sample size is not equal to sampling error. You need to use the precision instead. I mean, sampling error implies precision. And those funnel plots have been around a long time, and they're useful, but it's curious, even since 2000, there are all of these different methods. I mean, good grief, it's like 12 or 14 on this list. I'm not counting right now. And so even in 2000, we knew limitations of these different ways of looking at publication bias. So they all have limitations. And so one lesson about publication bias and meta-analysis, well, you can never really be sure, or can you? I'll come back to that as we get near the end of this talk. Eggers is one of the most popular methods out there, and they point out the statistical properties of the method are not described as in the original. I think since then there have been many people who've looked very carefully at it. In fact, in passing, I'll note that PET Ps is a version of Egger, builds on it, that's fairly popularly applied, and PET is essentially the very same thing. Ps is just the standard error squared. And there are some rules that they advocate about how you interpret the mean effect size with publication bias. Anyway, that's just, so if you want to look that up, I didn't put it in this talk, but go look up Tom Stanley and Ducoliados around 2014 or so. And anyway, and actually, Egger's test itself may be biased. And even if you do find asymmetry, the cause of the asymmetry is unknown. It might not be publication bias. It might be complications of the particular database, moderators that are not being assessed, perhaps. So how do you interpret funnel plots? And I would say these points are applicable to any publication bias test. I would say, first of all, you've got to be aware of moderators. And this is, of course, why I advocate topics plus M as a strategy in meta-analysis, because the plus M part is a priori, and you are thinking about, well, what possibly could be going on with this? I see my other talks about that. But anyway, the idea is under heterogeneity, there are subpopulations of effect sizes within the literature that you're examining. And so basically, publication bias tests are routinely assuming a single population of effect sizes. So they're not ideal for heterogeneous circumstances. Okay. Here's a classic on this point, Lau et al. 2006 again, the same. So here's a suspicious looking set of study results. Imagine some sort of, they say inhaled dysodium. It's a medical thing. I can't even pronounce that. And they found significant heterogeneity. So already I would say that's a caution. But imagine that those two distributions are broken out by younger and older children. That does look a little different already, doesn't it? And their point, I mean, they've got a fascinating title. They call it the case of the misleading funnel plot. So the overall funnel plot may not be that diagnostic. And maybe there are other things on, like maybe some of them are crossover designs where participants go from treatment to control and vice versa. Maybe they're parallel designs, the green dots. Those distributions also look quite different in here. So when we're thinking about funnel plots, we're thinking of publication bias in general, these things need to be accommodated. You should be thinking about your moderators along with publication bias patterns. Trim and fill has become an extremely popular test for publication bias. And so you can imagine a distribution. Here's from their original article in 2000. And I know parenthetically, Hedges and Vevea had a very similar test that just did not become as popular, perhaps because it didn't have software originally, and Duval and Tweedie did. So if you've got an actual raw distribution of effects that looks something like this, and the more precise ones are on top, and the less precise are on the bottom, we should see by sampling error that the ones down here are dispersed more, and that's exactly what this distribution shows, okay? But let's imagine a case of publication bias. It's going to look more like that. The null results, the reversals, so these are literally negative. Null results would be ones that are not different from the zero value, right? So in parlance, calling a trial that gets null results negative is just wrong. But so now trim and fill come in, and okay, now before we move on, think here's the overall effect. It's non-significant. This effect happens to make it. So that treatment or correlation or whatever it is, in this case it almost has to be a standardized mean difference we're looking at. So let's imagine treatments in this case. The treatment is showing to be significant here, p less than 0.05. And significant, eureka, we've got it. But boy, that's a suspicious looking distribution. It's asymmetric. So trim and fill can deduce what that shape should look like and fill them in, and now you've got what looks like the original effect size. Ta-da. So I mean, obviously, if you had all these effects observed, the trim and fill test would not need to intersperse anything. But because they're missing from the distribution in B, using trim and fill will do that. And the trim and fill statistic is fairly sophisticated. It will look for outliers, and outliers is another thing to be very alert to in your meta-analysis, because just one or two cases might force a test like this to indicate it, or eggers, or any of them. So beware of outliers. And you know, I've tried to encourage, like, if you get an effect size sign wrong, so imagine you calculated one over here in distribution A that was supposed to have a positive one. Well, that one is about 2 standard deviations different from where it should be. That could have dramatic effects on these tests. Okay. Anyway, trim and fill will detect, if this is too extreme of an outlier, it might chop it before making the distribution equal. So there are different versions of it. But okay, two points here. The fun part, well, the fun, one of these vexing problems of publication bias is, like, imagine distribution B. It might have I squared equals, 20 or something. And I don't know what it actually is here, and tau squared might be close to 0. Is that significant? Okay, you can do the test for Q and so on and find out, okay? But once you infer these tests down here, probably Q will be significant. And then you've got heterogeneity. So in fact, this distribution might imply more than one population of effects. And so you're back to that problem of, well, when do you trust publication biases? When you've got multiple population effects in your particular literature. So this is a problem with really across publication bias tests. And with this one in particular, trim and fill has been found to be overly sensitive. It detects too much publication bias, if you will. But I suppose that means that this estimate you get in the end is going to be more conservative, so maybe we like that. In 2019, along with Emily Hennessy, I advocated a practical strategy, or sometimes I call this a common sense strategy, to avoid publication bias. It rests on 2 strategies. It rests on 2 things. One is retrieve the unpublished papers and beware about the ones that are preprints and just going to become published in the next year or so. So you've got to retrieve the unpublished papers, and then you look at them in a contour enhanced. This is contour enhanced funnel plot. A lot of the software can do this now. And the key feature of a contour enhanced funnel plot is that you've introduced the contours for statistical significance. And so when you get over to those gray zones, you're getting to the point of statistical significance. So things that are in the white are non-significant. Things that get out here are significant. Okay, so put asterisks on those. And now what you're doing in this contour enhanced funnel plot is plotting the published studies, so that's published, and the unpublished studies with different symbols. I did this in Stata. I'm sure you could do it in R, and probably you could do it in other platforms too. And the point is that published and unpublished studies are not differing in terms of their statistical significance. And if you did a literal comparison of them in this case, I'm sure you would find that they're not different from each other. By the way, this distribution of effects in A is homogeneous. Okay. In this case, the same thing is true. It's the very same distribution. I've just changed the points so that now you can see that published studies are the ones that tend to be significant. That would be dramatic publication bias. Okay. And the ones that are non-significant are overwhelmingly unpublished. Okay. Now, more typically, as I've already implied, you're going to see things that are more like this, such that you've got a lot of variation going on. Again, a publication bias test is probably not helpful here because you've got more than one population of effects going on. And this is the more typical thing you see in meta-analysis. Now, one more point about contour-enhanced funnel plots. Sometimes you see them plotted over the mean effect size value, and the mean in value C here is going to be, what, around 0.25 or so. Sometimes you see the contours aligned around the mean value instead of the null value. If you're going to do it properly, you center it on the null. If you center those contours over the mean, now what you're detecting are studies that are outliers compared to the original, or to the overall mean, excuse me. So not advised, although some cases you might find that valuable, maybe for detecting outliers. More recently, Mather and van der Wiele have produced this interesting strategy. I think that it hasn't been evaluated very dramatically yet, but I like it in some ways. And it's becoming quite popular in recent reports. So what they do is similar to contour-enhanced funnel plots. They're drawing a line here for where the p less than 0.05 value is. And these are actual data that have to do with whether playing violent video games creates more violence. And so the overall estimate is right here, this diamond. My computer will cooperate. I'll get lines going around it. There it is. And so that's the overall effect. The ones that are statistically significant are shaded this beige color, right? And so those are now what you do is you look at the ones that didn't get the effect. These are null results, and average them, and you get this effect. You might imagine that as a worst case scenario for the effect of video games on violent behavior in this case. So what it's like literally a sensitivity analysis to see whether even in the non-significant results you get this basically the same pattern as in the ones that affirmed it statistically. Again, software is out there to be able to do this, so you can do this. All right, should you worry about publication bias? Should you worry about publication bias? And I raise this question because I think you probably would be aware if there is publication pressure for a particular phenomenon just by virtue of being a practicing scholar. Nowadays, you've got prediction derbies out there predicting whether an effect will replicate or not. So back in 1994, Behm and Honorton published this piece about ESP, and they ended up concluding that it exists. Would you worry about publication bias there? I think I would be worried about it in that instance. So in other instances, I don't think I would be as worried. I got a couple more examples. Sexual orientation and handedness. Okay, a lot of data available. Would you be interested in publication bias? I think it would depend on whether there was a popular hypothesis about it. It's been bandied about in the literature. People have talked about lefties being more likely to be sexual minorities, for example. So it might be connected to handedness. Well, if evidence ever comes out that's negative for that hypothesis, is there publication pressure against it? Maybe, okay? Another one, left-handedness is a marker for decreased survival fitness. Same thing. If there's concern, probably it's because these are small effect sizes that they're worrying about publication bias, right? There are things that cannot be seen easily. I think publication bias is going to be more important to resolve. And then a more extreme example, perhaps, and one I think is really compelling, as we start to get more and more meta-analyses of means. Well, the means in study reports, like this one, which is anxiety, Gene Twenge is the very first one I ever saw with means as an effect size, and I was dazzled by this. I think this is brilliant. Because the mean values of anxiety, like almost every other mean, are probably not censored for publication bias. When people publish results related to anxiety, for example, they're using it as a confounder, or they're using it as a predictor of something else. The publication pressure will be on those associations. It won't be on the mean values itself, or the standard deviation connected with the mean, which is needed for meta-analysis. So all of that's really good, and this makes analysis of means a whole different category for publication bias. It's very difficult to imagine how publication bias would matter for something like this. Okay. So as I said, now I came across this really interesting meta-analysis, and this is a strange example in a model of new modern research in the behavioral sciences, psychology related fields. Here's a meta-analysis related to a literature of studies, experiments that look at mate priming, and then study the risky behavior of the results. So they expose men to attractive, photos of attractive women, and then they see how risky they are in a subsequent task. And you can see across this literature, you've seen enough forest plots in this class by this point. Wow, these are all lining up so well with the effect. The overall effect is 0.57, so it's a medium effect size. If you saw people in these studies, you could probably tell with the naked eye. You don't need statistics when the effect size gets big enough. So this looks beautiful. Looks like robust evidence in favor across these 43 studies. It's homogeneous according to the results. I actually downloaded the data. I could not replicate that result, but no matter. Now they go ahead and apply Egger's test to it, and they conduct a bunch of replications, and some of them are pre-registered, unlike a lot of these older studies. So I mean, it goes all the way back to 2004, and this is now into about 10 years later when this article comes out. So I'll show you all the results in one place. Here's a beautiful example showing you contour-enhanced funnel plots along with Egger's regression line is added in here. These dots over here are all the replications. Okay, and they've given you a lot of studies will do this too. They'll give limits right around the mean, which I've applied as a way you can do it, and you can see the shape is exactly that of the contour-enhanced funnel plot. Applying some of these are outliers compared to the original, but whatever. So first, let's look at the distribution of effects. This is a dramatic indication of possible publication bias. So Egger's regression test for publication bias, so this is Egger. This slope is literally significant, so p less than whatever, 0.05, 0.01, something like that. And what they've done is they put the regression line on. So on the bottom here, this is how you do it, back to contour-enhanced and funnel plots in general. You're putting the effect size as the x value, the x-axis. The standard error is on the y. It's kind of turning things on its head, but that's how it works. So this is the best fitting line, this red thing, and where it intersects 0 up here, that's the value that you would expect for this kind of intervention to get if the standard error, the precision, was equal to 0. Well, when do you get a standard error of 0? When you have an infinite population size. So what you're seeing is that this is a projection, and whatever confidence interval they have around it would be a projection to an idealized world where you can have an infinite sample of people in it. And that, they don't give us the confidence interval for that, but you can see that it would include the value of 0 almost certainly, because look at it projecting into this other distribution of effects that all are null, and none of these replications could follow up and find the same pattern that the published studies were finding. So I would suggest that probably this is the hypothesis death knell, though I'm curious what has happened after this, and I'm not in this literature, so I really can't say. But this is really remarkable statistical work and a beautiful picture to show if there's publication in a literature, this looks pretty darn damning. Okay, two very doubtful strategies. I'll draw some light to these because I don't want you to use them. In parlance, we often put the non-significant results in a file drawer. This is a very 1950s kind of expression, but the file drawer effect is another name for publication bias. And literally the unpublished results would find in someone's lab folders like that. Well, failsafe n came along and it projects what the mean effect size for a meta-analysis would be using either the p-values or there's a version for the actual magnitude of the effect size. It projects how many file drawer studies you'd have to find in order to make the effect non-significant. So if the value is like 10,000 or something, well, that's implausible. There could be that many studies, and therefore the effect exists. But the problem is there's no distribution for this statistic, so we don't know what it means to have a value of 20,000 or something like that. We don't know how frequent it is. We also, the test really assumes null effects, so you'd have effects averaging 0 rather than ones that reverse the effect. So if you have a lot of opposing effects in the literature, this would be, it would correct the effect size even faster and make it null or even reverse it. So again, there's so many better ways to evaluate publication bias. Don't use it. Don't use it. Out. Right? The other one that I'll introduce is probably doubtful or very doubtful, relates to p-hacking. Now, here we are worshiping this convention of, it's another one of those cases of a silly norm that just kind of took off and got too powerful. A researcher gets an effect of 0.051, so it's going to reject the, it's going to not accept the alternative hypothesis. You should accept the null in this case, asking for advice. And he says, well, you can do all these other tests, right? And eventually you'll find one that gives you less than 0.05. And that's the one you publish. See, that's p-hacking, people. And related to that, a p-curve strategy has emerged. And in this, what you're doing is examining whether the distribution of p-values in the studies exceeds that expected by different norms. So one of these is a power line and the other is a alpha line. So in this case, it looks like they're p-hacking because you shouldn't expect the tail of that distribution to go up. The tail should go swooping down instead of swooping up. That would suggest a pattern of p-hacking. Now, the problem with it is it doesn't handle heterogeneity. In fact, we could say that about the file drawer analysis too. Again, you've got more than one effect size going on in a distribution. Why are you using these statistics? Right? Maybe it makes sense in cases where it's a very narrow literature of studies that are very, very similar to each other. Now, let's say that everything points to publication bias. Is that a death sentence for that literature? It's just, hopelessly biased. Are the effect size estimates, too biased to be of any use? But the question I would ask you is, are there significant moderators? If there are, publication bias must be much more complex to explain it away. You need a much more complicated theory than just pure publication pressure. It have to do with the combination of a study having all women or all men or whatever the moderators are, and wow, you get the significant effect of men. It's a gender effect, people. So again, the publication bias can be disguised as something else. Right? And put another way, our studies have supported a particular moderator pattern more likely to get published. So this would be a much more complicated problem. And as I've been saying all along, is that you might see publication bias, but alongside heterogeneity that's due to other sources. So it's not necessarily publication bias can exist along with other effects. So here's what I would recommend is that you model publication bias along with instead of overall, especially under heterogeneity. So here's a case where Stern and Egger have shown us that the standard error is significantly associated. This is literally small error effects. If you know that basically large standard errors are small studies or small sample sizes. And small standard errors are large effect sizes. And so you've got a linkage. This looks like publication bias. And this is what I would call a bivariate, not univariate, but that's me. Because there's two variables in it. So these are not simultaneously in there. And they've got a true moderator here, low versus high contact. This meta-analysis is looking at teacher expectancy effect. So teachers told the students are all brilliant to know how much does that affect actual performance. Well, maybe you have high contact versus low with the teachers, and that is significantly related with the effects. That you have more contact, therefore there's a bigger effect size. If you put them in the same, I would call this a multiple moderator meta-regression. Now, look what happened. The standard error effect is no longer significant, but the contact one remains significant. So here's a case where publication bias looks serious, but it turns out not to be a problem. The better theory about this particular meta-analysis is that the true moderator explains away the effect. You wouldn't think there's a publication bias in this case, although you could ask whether these two factors could interact, and that would be an even more refined. If you've got enough studies, you could do that as well to make sure that there isn't some sort of interaction going on between the two. And if there is, you've got to interpret it. Now, some conclusions. I said that these are vexing issues, and I haven't even ventured into the problem back here of side effects. You should do meta-analyses of the side effects too, okay? But, all right, scientific practice is biased, all right? You have to conclude that. But that doesn't mean that there's no truth in it, okay? I'm a true believer. The second one overall is that detecting publication bias in meta-analysis is fraud. This is a really difficult thing to do. The fact that confounding exists means that a pure publication bias pattern is going to be rare. Now, one thing I didn't say directly, but you should get it in all my other talks. I keep talking about triangulation. It's a convention these days, use multiple strategies to triangulate on whether there's publication bias. And be alert that there are new strategies emerging all the time. I mean, that 2000 paper had 12 or 14, and by now there must be twice that. So they're emerging all the time. This talk is basically an introduction to the subject. And I also haven't even sent you out directly to websites that show you how to do it, but you can find them pretty easily. And then the recommendation that I'm leaving you with is that especially when you have heterogeneity, which is almost always the case, you have large meta-analyses, it's almost always the case they're going to be heterogeneous outcomes. You should be modeling publication bias along with moderators. You should have a priori moderators as topics plus M, and you should have publication bias as perhaps a sensitivity analysis near the end. Conventionally, meta-analyses these days tend to put it either at the beginning of the results section, publication bias, or at the end. I'm not sure it makes sense as an overall strategy because of the heterogeneity problem. If you determine that there are multiple, that you've got true effects, that there are multiple populations going on here, why are you using something that assumes one population? Model, if you're going to go after publication bias, I think you have to be more sophisticated. So, some discussion questions. What are reasons that a primary level research study is published? The Greenwald paper kind of hints at the problems that emerge from the time you collect data to the point you might publish. What are reasons it's not published? I mean, part of it could be significance. There might be other reasons. I mean, your motivation, for example. Be meta-scientific about this for a little while and think, is it just the quality of the methods? That's a whole other talk. How can you be certain as a meta-analyst that you have publication bias in the literature? Have you eliminated the possibility of moderator effects? And how does heterogeneity affect the picture? Because moderators are what you're going to want in a heterogeneous literature. That's where the action is. And of course, I'm going to talk about that as well. All right, enough on this subject. Have a great day.